Hello friends, welcome to this lecture. In this lecture we will discuss the Frobenius series solution method for linear second order ordinary differential equation, and we have already discussed the power series solution method for second order linear differential equation. Here we extend our, or here we continue our discussion for the equation where this point is a singular point. So, consider the differential equation Ly Pt d2y by dt square plus Qt dy by dt plus Rty equal to 0. Here Pt is a coefficient of y double dash, Qt is a coefficient of y dash, and Rt is a coefficient of y. So, here we say that a point t equal to t naught is a singular point of this differential equation given as equation number 1 if Pt naught is equal to 0. So, if Pt naught is not equal to 0 for t equal to t naught, we say that t naught is an ordinary point of this differential equation, but in place when t equal to t naught, if Pt naught is equal to 0, we say that the point t equal to t naught is a singular point of this differential equation, and solution of 1 often be unbounded in a neighborhood of the singular point t naught. So, in general we cannot apply the power series solution method for the equation or near the point where solution is a singular differential equation. So, here we say that solution of 1 may not be continuous and the method of power series solution will not work in some cases. So, our goal is to find out a class of singular equations which we can solve for t in a neighborhood of the singular point t naught. So, first let us say define the easiest singular differential equation which is known as Euler Cauchy Euler equation. So, here the differential equation Ly given as t square d2y by dt square plus alpha t dy by dt plus beta y equal to 0. Here alpha and beta are constant and this equation is known as Euler's equation. If you look at here, the coefficient of y double dash is t square and t square will vanish at t equal to 0. So, it means that for this equation this t equal to 0 is a singular point. So, here we say that here in general we cannot we should not apply power series solution. So, in place of power series solution, what should be the method by which we can find out the solution. So, here we first try to solve this Cauchy Euler's equation, and with the help of working procedure here for this particular problem, we try to extend this theory for a general ordinary differential equation where t equal to t naught is a singular point. So, here we assume first of all that without loss of generality that t is greater than 0 here, and we may observe that t square y double dash and t y dash are both multiple of t to the power r. So, if y equal to t r, then you can easily calculate y dash. So, y dash t is equal to r t to the power r minus 1 and y double dash t is equal to r minus 1 t to the power r minus 2. So, we can say that if we multiply t in y dash, then it will be what? So, it is what? R t to the power r, and if you multiply t square here, then it is what? R into r minus 1 t to the power r here. So, we can say that this if yt is equal to t to the power r, then t y dash t is equal to r t to the power r, and t square y double dash t is r into r minus 1 into t to the power r. So, it means that this component and this component is multiple of t to the power r. So, we can say that this can be written as when if y equal to t to the power r, then this equation can be written as some kind of polynomial in terms of r into t to the power r equal to 0 as a solution. So, it means that if t to the power r is non-zero, we already know that this t to the power r is non-zero. So, it means that y equal to t to the power r is a solution of this equation provided that f of r is equal to 0. So, this is the summary of this method that we want to find out. We want to find out the values r for which t to the power r is a solution of this particular equation which is known as Euler's equation. So, we may try y equal to t to the power r as a solution of 2. So, for that you just calculate first derivative of t to power r, which is nothing but r t to power r minus 1, and second derivative of t to power r, that is r into r minus 1 into t to power r minus 2 here, and simply we put y equal to t to power r in our equation, that is Ly equal to t square d2y by dt square plus alpha t dy by dt plus beta y equal to 0. So, in place of y, let us put t to power r. So, L of t to power r is going to be r into r minus 1 t to power r plus alpha r t to power r plus beta into t to power r. So, if you simplify, we have this equation, that is r into r minus 1 plus alpha r plus beta into t to power r. So, let us denote this equation, quadratic equation, in terms of r as f of r. So, f of r into t to power r. So, L of t to power r is given as f r t to power r. So, we say that here f of r is known as initial equation, and it is given as r into r minus 1 plus alpha r plus beta. We can simplify and we can have f r as this initial equation, that is r square plus alpha minus 1 r plus beta. So, we can say that this LTR is equal to 0 provided that f of r is equal to 0. So, it means that y equal to t to power r is a solution of 2 if and only if r is a solution of the quadratic equation, that is r square plus alpha minus r alpha minus 1 into r plus beta equal to 0. That is that r should satisfy this quadratic equation, that is f r equal to 0 here. So, let us find out for what values this f of r is equal to 0. For that, we can use the theory of quadratic equation, and we can find out the roots as r1 and r2, where r1 is given as minus 1 by 2 alpha minus 1 plus under root alpha minus 1 whole square minus 4 beta, and r2 is the other root, that is minus 1 by 2 alpha minus 1 minus beta minus under root alpha minus 1 whole square minus 4 beta. So, here we are able to find out this r1 r2 as root of this equation, that is f of r equal to 0 here. So, here we say that as similar to case of constant coefficient, we have to consider the 3 cases where it depend on this quantity, that is alpha minus 1 whole square minus 4 beta, whether it is positive, negative and equal to 0. So, here let us consider all these cases, and depending on these cases our solution will be t to power r is a solution, and r is taking these two values r1 and r2, and depending on this quantity whether it is positive, negative and 0, we will find out the solutions here. So, let us say case 1 where we have this alpha minus 1 whole square minus 4 beta is greater than 0. So, here if you look at this quantity in square root, this quantity is positive. So, it means that now we have two different value of r1 and r2, that is r1 is equal to minus 1 by 2 alpha minus 1 plus some quantity which you can easily calculate by taking the square root of this. So, here we can say that in this case equation 5 has two real unequal roots, and thus 2 has two solution of the form y1 t equal to t to power r1 and y2 t equal to t to power r2. So, here r1 and r2 is not equal, real, and it satisfies the equation f r equal to 0, and we can say that your y1 solution is given as t to power r1 and another solution is given as t to power r2, and we can easily check that these two obtained solution are linearly independent solution, because we already know that we can easily check y1 t upon y2 t is equal to t to power r1 minus r2. So, it means that the ratio of these two is not constant. So, we can say that y1 and y2 t is y1 and y2 are linearly independent solutions. So, if r1 is not equal to r2, we can say that y1 t equal to t to power r1 and y2 t equal to t to power r2 are linearly independent solutions. So, we can write our general solution like this: yt equal to c1 t to power r1 plus c2 t to power r2. Here please note down that here we are assuming that t is greater than 0. Now, consider the second case, but before that let us take one example based on this theory. So, find the general solution of this equation t square d2y by dt square plus 4t dy by dt plus 2y equal to 0. We denote this part as some equation Ly equal to 0. So, here as we have discussed that let us put y equal to t to the power r, because it is satisfying the Cauchy Euler equation. So, it is a Cauchy Euler equation. Here alpha is equal to 4 and beta is equal to 2. So, when you put y equal to t to the power r, we can simplify this r into r minus 1 t to the power r plus 4 r t to the power r plus 2 t to the power r. So, taking the coefficient of t to the power r as r into r minus 1 plus 4 r plus 2, and if you simplify this, it is r square plus 3 r plus 2, and you can factor it out, and we have r plus 1 into r plus 2 t to the power r. So, it means that t to the power r will be a solution of this if r equal to minus 1, and you can call it r 1 and r 2 is equal to minus 2. So, here we have r 1 equal to minus 1 and r 2 equal to minus 2, and we can write down our general solution as y t as c 1 t to the power r 1, that is minus 1, plus c 2 t to the power minus 2, that is r 2, because of this thing. So, here we have general solution c 1 by t plus c 2 by t square is the general solution of this equation number 6 here. Now, moving on case 2, here we have this alpha minus 1 whole square minus 4 beta equal to 0. So, in this particular case we have equal real roots, that is r 1 equal to r 2 equal to 1 minus alpha by 2. So, here when r 1 is equal to r 2, we have only one solution available, that is y t, y 1 t you can call it as t to the power r 1, whether you use r 1 or r 2, because r 1 and r 2 are equal. So, we have only one linearly independent solution. So, how to find out the second solution? We already know that this method of reduction is used to find out the second solution. So, but here method of reduction is what? You assume that y 2 t is equal to some function c t y 1 t, and we try to find out the function c t in a way that this y 2 t satisfy the given ordinary differential equation. So, this process is based on method of variation of parameter, and by using this we actually get a linear differential equation of one order less. That is why this method is known as method of reduction also. So, here we will not use this method of reduction here. Here we will give us an alternative method to find out this y 2. Why we are giving this alternative method? Because this method we will going to generalize for a general singular ordinary differential equation. So, let us observe that this f of r, which is given as r minus r 1 whole square, because here r 1 is a double root. So, in this case we can write L of t to the power r is equal to r minus r 1 whole square into t to the power r. So, we already know that r 1 satisfy this equation, and we have a one solution, that is t to the power r. So, here we simply say that if we take the partial derivative of this equation number 7 with respect to r, what we will get? Divided by divided r of L t to the power r equal to L divided by divided r t to the power r. If you look at L is what? L represent an operator equation. If you look at here, L represent this kind of equation. Ly is t square d2y by dt square plus alpha t dy by dt plus beta y. So, here we can say that this is an operator which input is y and output is this quantity t square d2y by dt square plus alpha t dy by dt plus beta y. So, here if you look at, this is a differential operator given in terms of d by dt. So, here we are differentiating with respect to t. So, here in this procedure we are applying the partial derivative with respect to r. So, since it is this L is independent of r, so we can take this derivative, partial derivative inside. So, we can write this as divided by divided r L of t r can be written as L of divided by divided r of t to the power r. So, and if you look at the right hand side, it is divided by divided r of this quantity r minus r 1 whole square t to the power r. So, let us see what it will give us. So, here we already know that divided by divided of r of t to the power r is nothing but t to the power r ln t, that you can easily verify. So, here if you take y equal to t to the power r, then apply the logarithm, and you can easily differentiate with respect to r, with respect to r here. So, here using this expression divided by del r of t to power r, t to power r ln t, we can write this left hand side, that is here you simply write this is what, t to power r ln t equal to, so L of this quantity is equal to, if you differentiate this, what you will get, 2 r minus r 1 t to power r plus r minus r 1 whole square, and again t to power r ln t here. So, we will get this expression for t to power r ln t. So, L t to power r ln t is equal to r minus r 1 square t to power r ln t plus 2 r minus r 1 t to power r. We know that if you look at the right hand side, if you put r equal to r 1, then this right hand side will be 0. So, it means that this t to power r 1 ln t is a function, if we put in place of y as t to power r 1 ln t, then we have 0 for this operator equation. So, it means that when we consider this Ly equal to 0, we say that y equal to y1 is a solution of this operator equation if L of y1 is coming out to be 0 here. So, we can say that y1 is a solution of this equation. So, here we say that L of t to power r1 ln t is equal to 0. So, it means that this t to power r1 ln t is another solution of the differential equation Ly equal to 0. So, here we say that since t to power r1 and t to power r1 ln t are linearly independent. So, we can say that in this case the general solution of 2 we have yt equal to c1 plus c2 ln t t to power r. So, in case of equal roots, our solution is given by this, that yt equal to c1 plus c2 ln t into t to power r, and we can easily check that this I am leaving it to you, that t to power r1 and t to power r1 ln t are linearly independent solutions. So, this I am leaving it to you. So, now let us take one example based on this. So, here we consider this linear second order ordinary differential equation Ly equal to t square d2y by dt square minus 5t dy by dt plus 9y equal to 0. So, this is an Cauchy Euler equation. So, we apply it y equal to t to power r and try to find out the values of r for which it has a solution as t to power r. So, when we apply L as t to power r, we will have this r square minus 6r plus 9 into t to power r. Which we can simplify as r minus 3 whole square t to power r. So, it means that this t to power r will give a 0 of this provided r is equal to 3. So, it means that corresponding to r equal to 3, we have a one solution. So, we say y1 t equal to t to power q as one solution, and as we pointed out that if t cube is a solution, then t cube ln t will also be a solution, because here r equal to 3 is a double root of this initial equation, this equation. So, in case of double root, we have one solution as t to power q as it is, and second solution is given as t cube ln t. So, here our general solution is yt equal to c1 plus c2 ln t into t to power q, where t is greater than 0 here. So, again you may take this as an exercise that if you assume y2 t as equal to ct into t to power cube, and if you put it here, then you can easily find out y2 dash t is equal to c dash t t cube plus 3t square ct, and similarly you can find out y2 double dash t as c double dash t t cube plus c dash t 3t square plus 6t ct plus 3t square c dash t. If you put it back and solve, you can easily find out a differential equation in terms of ct, and then also you can get a solution given as t cube into ln t. So, you try it. So, now consider the last case, that is case 3. Here we have alpha minus 1 whole square minus 4 beta less than 0. So, in this case r1 and r2 are coming out to be complex root of the differential of this quadratic equation. So, here we have r1 as lambda plus I mu and r2 equal to lambda minus I mu, where lambda is given as 1 minus alpha by 2 and mu is given as square root of 4 beta minus alpha minus 1 whole square divided by 2. So, here we are getting a complex roots, but since this differential equation represent a real world phenomena. So, it means that we must have real solution. In fact, we are really interested in real world solution. So, out of this complex solution, let us find out the real solution. So, here solution will be what? Phi t equal to t to power r should be a solution. What is r here? Here let me write it r as lambda plus I mu, and we can write this as t to power lambda into t to power I mu. The problem is that this t to power I mu may not be defined. So, here to define this t to power I mu, let us write t as e to power ln t. So, if you calculate e to power ln t, it will give you t. So, we write t to power I mu as e to power ln t to power I mu. Now, this has a meaning. So, here we can write t to power lambda into e to power I mu ln t. So, we already have this expression e to power I x as cos of x plus I sin x. So, using this expression, we can write down our solution as t to power lambda cos of mu ln t plus I sin mu ln t, and we can say that this is one complex valued solution of the equation which is known as Cauchy-Euler's equation. So, since we are not interested in this complex solution, so here we take out the real part and complex part out, and we can say that this y1 t, that is real part of phi t, that is t to power lambda cos mu ln t, and y2 t as imaginary of phi t, that is t to power lambda sin mu ln t, are two real valued independent solution of 2. So, it means that if we have a complex root of a differential equation, then its real and imaginary part will also satisfy that real ordinary differential equation. So, using that result, we can say that real part of phi t and imaginary part of phi t are two real valued independent solution of 2, and we can write down our general solution as t to power lambda c1 cos mu ln t plus c2 sin mu ln t, and in this way we can write down the solution. Now, let us take one example based on this. So, here we take Ly as t square d2y by dt square minus 5t dy by dt plus 25y equal to 0. Please remember, in case of Cauchy-Euler equation, the order of derivative is 2 here, and here power of t is 2. So, we can say that if we can write down this equation. So, here we write that alpha k t to power k dky by dt k equal to 0. Here k is equal to say 0 to any number n is known as Cauchy-Euler equation of order n. So, here we say that the order present in derivative is multiplied by t to power that same order. So, here we have d2y by dt square, then it is multiplied by t square. Here we have dy by dt, then it is multiplied by t into some constant, and here we do not have any derivative. So, here t to power 0 is there. So, we can write that this is a simple Cauchy-Euler equation. So, let us take y equal to t to power r as a solution here, and when you put L equal to t to power r, it is given as r square minus 6r plus 25 into t to power r. When we take the 0 of this, then we have 0 r 3 plus minus 4i. So, it means that phi t is given as t to power 3 plus 4i, and I can write this as t cube into t to power 4i, but t to power 4i is not defined in this current situation. So, here we write t as e to power ln t to power 4i, and we can write t cube into e to power 4i ln t, and this here using this formula e to power I x, we can write t cube cos of 4 ln t plus I sin 4 ln t, and taking out the real part and imaginary part, we can write y1 t as t cube cos 4 ln t and y2 t is t cube sin 4 ln t are two independent solution of 11. So, here general solution is given as y t equal to t to power cube c1 cos 4 ln t plus c2 sin 4 ln t and t greater than 0. So, we have discussed the solution of this equation Ly equal to d2y by dt square plus alpha t square dy by dt plus beta, here we have only y equal to 0, and here this is a Cauchy equation, and we say that y t equal to t to the power r is a solution provided that this r satisfy this equation f of r equal to 0 here, because when put y t equal to t to the power r, then L of t to the power r is given as f of r into t to the power r. So, this will be a 0 when f of r equal to 0. So, here we are trying to find out the real roots of r1 and r2, and once we have roots r1 and r2, then accordingly we can find out the solution of this equation. So, now so far we have utilized only the case when t is positive. Now, let us consider the case when t is not positive. It may be the value t less than 0. So, here in case when t is less than 0, one main difficulty is that t to the power r may not be defined in the neighborhood of t equal to 0, and another difficulty is that this ln t may not be defined, because ln t is defined only for positive values. So, it may not be defined for negative t. So, so it means that whatever we have already discussed may not be applicable in the case when t is less than 0. So, here we will do one simple thing. We simply handle these difficulties by taking the change of variable, and here we write t as minus of x. Since t is negative, so this x is going to be a positive. Now, using this change of variable, let us calculate dy by dt. Dy by dt equal to du by dx, where what is u here? Here we write y t is equal to u of x. Here x is positive. So, here so here we are assuming that y t is equal to u of x here. So, t is equal to minus x, here x is positive because t is negative. So, dy by dt equal to du by dx and dx by dt. On dx by dt you can easily calculate from this, that is coming out to be minus 1. So, dy by dt equal to minus du by dx. Similarly, we can calculate d2y by dt square, that is d by dt of minus du by dx, and which is nothing but d by dx of minus du by dx into dx by dt. And if you simplify, we have d2u by dx square. So, we have dy by dt as minus du by dx and d2y by dt square as d2u by dx square. So, we can write this equation minus x square d2y by dx square plus alpha times t is minus x minus du by dx plus beta u equal to 0. And if you simplify, you will have this equation x square d2 by dx square plus alpha x du by dx plus beta u equal to 0. Here x is positive. And if you look at carefully this equation number 12, then it is exactly the same as 2. Here 2 is what? Here t e square y double dash t plus alpha t sorry. So, here we have alpha t dy by dt plus beta y equal to 0. So, if you look at, and here we have assumed that t is greater than 0. So, if you look at these two equations, then it is exactly the same. The only thing is that u is now y is replaced by u and t is replaced by x, and we already know how to find out the solution. So, in this case solution is given by u of x depending on the discriminant which is positive, negative and 0. So, here when it is positive, we have solution C1 x to the power r1 plus C2 x to the power r2, and in case of equal root we have C1 plus C2 ln x into x to the power r1, and in case of when discriminant is negative, we have a general solution as C1 cos mu ln x plus C2 sin mu ln x into x to the power lambda. So, depending on the whether this alpha minus 1 whole square minus 4 beta is positive, 0 or negative. So, if we summarize the solution given in this case when x is greater than 0, or we can say that t is less than 0. So, in this case we can say that x is written as minus t, this I can write it modulus of t. So, it means that if we combine the general solution given in case t positive and t negative, we can write down the solution is given as C1 modulus of t to the power r1 plus C2 modulus of t to the power r2 when discriminant is positive, and in discriminant 0 we have C1 plus C2 ln modulus of t into modulus of t to the power r1, and third case C1 cos mu ln modulus t plus C2 sin mu ln modulus t into modulus t to power lambda. Here in this case your discriminant is negative. So, in this case it means that we have solved this Cauchy-Euler equation assuming that y equal to t to the power r is a solution. In fact, how to get this t to the power r? Here we can say that there are two way by which we can say that t to the power r is a solution. One is resemblance of constant coefficient case. Here if you look at the constant coefficient case is what? Here y double dash plus you can simply write some alpha y double dash plus beta y dash plus gamma y equal to 0. So, this is a simple linear second order differential equation and we know how to solve this. Here alpha beta gamma are constant. Here we have assumed that e to the power say r is a solution of this, because while putting this e to the power r here as a quantity, we can say that this is nothing but coming out to be f of r into e to the power r equal to 0. So, now this e to the power r is not a is not 0. So, we can say that this e to the power r t is a solution provided that r satisfy this equation f of r equal to 0. So, if you look at this Cauchy-Euler equation has exactly the similar situation. The only thing is that in place of e to the power r t we have here solution as t to the power r, and here when you put t to the power r here and then also it is coming out to be f of r into t to the power r equal to 0. So, this t to the power r will be a solution provided that r satisfy this equation, that is f of r equal to 0. So, this is say analogous to your constant coefficient case. So, here I am not going to discuss this, but I am saying that the same t to the power r you can get if you use the power series solution method. So, here if we consider this as a case of power series solution and we here we apply the power series solution, then you will see that we will get this t to the power r kind of a solution. So, I may give you this assignment that find out that y t equal to t to the power r is a solution if we apply the power series solution for this case also. Here this t equal to 0 is not a ordinary point, it is a singular point, but still here your power series solution will work out, and we get that t to the power r is a solution here. Now, let us generalize this finding to a more general differential equation. So, now our aim is to find a class of singular differential equation which is more general than Euler's equation. So, Euler equation is if you remember, it is t square d2y by dt square plus alpha t dy by dt plus beta y equal to 0. So, here we can easily check that t equal to 0 is a singular point of this differential equation, because this coefficient of d2y by dt square is coming out to be 0. So, at t equal to 0 is a singular point of this differential equation, but we know how to solve this, and so let us see. This can be written as this form d2y by dt square plus alpha by t dy by dt plus beta by t square y equal to 0. So, in place of alpha by t and beta by t square, let us replace this by function of t and function of so this alpha by t I am writing pt and beta by t square I am writing as qt. So, we can say that this 14 is a particular case of 16 provided that pt is equal to alpha by t and qt is beta by t square. Now, let us say that let us consider a more general case when this pt is not only p naught by t, but it is p naught by t plus p1 plus p2 t plus p3 t square and so on. So, here you can say that this is nothing but we have a power series solution, we are we are adding here. Similarly, in qt and not only q naught by t square term is there, but we have q1 by t plus q2 plus q3 t plus q4 t square is there. So, here we are adding some more terms which are coming from some kind of power series. So, here we can say that this 17 and 18 can be written in a way such that if you simplify this, then it is what t of pt is equal to summation some ak t to the power k, k is from 0 to infinity. Similarly, your t square qt is again written as bk t to the power k, k is from 0 to infinity. So, here we can we claim that the method which we have already discussed can be generalized for this kind of equation this kind of equation Ly equal to d2y by dt square plus pt dy by dt plus qt y equal to 0, provided that pt is more general than this alpha by t and beta by t square, or we can say that when tpt is given as this kind of power series, or we can say that when tpt has a Taylor series expansion at t equal to 0. Similarly, t square qt has a Taylor series expansion at t equal to 0. So, we can say that the expression 16 is said to have a regular singular point at t equal to 0 if pt and qt have series expansion of the form 17. In equivalent sense, t equal to 0 is a regular singular point of 16 if the function tpt and t square qt are analytic at t equal to 0. So, we can say that this is the situation at t equal to 0. So, at t equal to 0, first thing it should be a singular point. Second, that this tpt and t square qt must have Taylor series expansion at near t equal to 0. So, in this case we call t equal to 0 as a regular singular point, and in general for t equal to t naught we say that equation 16 is said to have a regular singular point at t equal to t1 if the function t minus t naught into pt and t minus t naught whole square qt are analytic at t equal to t naught, or analytic means t minus t naught into pt has a Taylor series expansion and t minus t naught whole square qt has a Taylor series expansion at a point t equal to t naught, and a singular point of 16 which is not regular is called irregular singular point. So, here I will stop here, and in next lecture we will continue the discussion of how to find out a solution for a regular singular point case. So, here I will stop, we will meet in next lecture. Thank you for listening us. Thank you.